How do we take a complex PDF datasheet and automate a fractured symbol set and PCB footprint land pattern model in a fraction of the time? With the most advanced PDF datasheet extraction in the industry, let's bring up a complex microcontroller PDF datasheet from Texas Instruments. Indexing into the PDF datasheet and selecting the pin description table, we can extract diagrams such as this BGA map or this flat pack diagram, or tables such as this multi-pin diagram table. Let's extract the first page of this table with the PDF datasheet table extraction. Next, we will complete the table extraction, turning it into a PDF template, and finally tag the rows which we wish to ignore on data transfer. Selecting Export, I will transfer the content from the PDF datasheet to the Scratchpad spreadsheet. Moving to the second page of content and invoking the table extraction, completing the table with the build PDF template, and copying the tags over from the previous PDF template. I will now export the content from the PDF datasheet to the Scratchpad spreadsheet. Moving to the third page of content, I will first create a PDF table and then build the table to a PDF template, copying over the previous tags from the previous page of content, and finally transferring the third page of content to the Scratchpad spreadsheet. Let's now move to the fourth and last page of content. I will first create a PDF table and then build a PDF template from that table, copying the tags from the previous page of content. And finally, I will export the last page of content to the Scratchpad spreadsheet. Moving to the Scratchpad spreadsheet, I now have the assembled 4 pages of content. We're now ready to tag the columns of the Scratchpad spreadsheet to give them very specific meaning, such as pin name, pin direction, and pin number. On this particular data sheet, 2 options exist for pin direction: the columns containing the I/O or the entire string of text. Let's now transfer the content from the Scratchpad spreadsheet to the main spreadsheet. We have many accelerator commands for datasheet mapping. Under Pin Tools, selecting Direction Code from String will automate the direction code from a string of text. Rechecking the datasheet, I now have several warnings due to duplicate pin names. Now that all the errors have been resolved, I have an extracted spreadsheet containing 111 pins. But the PDF document specifies 113 pins. How do I find that discrepancy? Let's select the Configuration button and move to the FootprintBuilder, where I have the industry's most complete set of footprint calculators and generators, including circular connectors, DBs, DB right angles, duals, shrouded headers, BGAs, chip arrays, chips, CQFPs, crystals, diodes, LCCs, LGAs, molded, oscillators, QFNs and Ps, SODs, SOICs, Js, Ns, and Ps, and SOTs and TOs, through-hole devices, including caps, resistors, fuses, inductors, LEDs, and TOCs, and variant calculators for very specific purposes such as dual row QFN packages. Let's move back to the surface mount category, selecting the BGA Calculator, where I have both user-defined settings and IPC 7351 calculator settings, nominal, minimum, and maximum value settings. I will first move to the Component tab and change the number of rows to 12 and 12, turning fiducials off, changing the pin pitch to 0.5 and ball size to 0.30, and recalculating. I will use the on-screen associative editor to click directly on the value, changing the mode to minimum and maximum setting, and entering the value directly on the screen, updating the side form entry automatically. Let's click on the B nominal value, performing the same functions. Bringing up the PDF document, we have the C3 pin appearing on the left side, and on the top view will appear on the right side. Changing the body orientation and selecting Generate will put the C3 pin in the proper orientation. I will now select a set of pins to become non-propagated. Completing the outer rows, I will now select the set of inner rows. And going back and referencing the PDF document, I will notice that the C3 pin is propagated in the array. Making the last two changes, I will move to the pin tools, where I will change the propagation to non-propagated for the selected set of pins. We have now completed the modeling of the BGA footprint part and ready to annotate from the schematic symbol spreadsheet to the footprint view. Once annotated, let's bring up the reporting and obtain a graphical report of all terminals with missing pin assignments. These two discrepancies are the missing pins in the original TI PDF datasheet. Contacting the component manufacturer, the two missing pins are ground pins, which I will manually add to the spreadsheet. Rechecking the datasheet, I now have 113 pins. Now that we have an exact match of the spreadsheet to the footprint, let's move to the symbol partitioner. First selecting sorting, and sorting by pin name, and then pin direction. Next, let's select the drag and drop to select the set of input pins, putting them on the left side, and the P1 to 6, putting them on the left side, and the remaining input pins at the top of the view by selecting the set of groups and pushing down all remaining pins as I drop the selected set. Let's take the set of bidirectional P pins and move those set of pins to the left side below the set of input pins. Moving to the output pins, let's take the COM0 and put it on the right side, and the set of output P pins, moving those in alignment with the input pins from the left side. Taking the S pins, and let's reorder the S pins, high to low versus low to high, and place those on the right side. And the X out and other remaining output pins to the right side. The power, grounds, and no connects, let's put on the second symbol fracture, created automatically with the next command. Putting the power on the left, the ground on the left, and the reserve pins on the right side. The reserve pins are all tagged as ground pins, or we could retoggle the pin destination to no connects. Resizing the window views, let's take the selected set of pins containing the no connects and cross-reference them to the footprint with the probe command, demonstrating the integration of the schematic symbol model to the footprint. Moving back to the main spreadsheet under File, selecting Current Part View, I will now attach and link the footprint model to the schematic symbol model. I'm now ready to export the part directly to my EDA tooling system. Under Exports, there's a host of EDA system exports, including OrCAD Capture, Allegro DE-HDL, DX Designer, PASLogic, and Design View. In this case, I will export to OrCAD Capture, saving the part and exporting directly to OrCAD Capture. Bringing up the library with the Open Library and importing the library, I now have the completed part directly exported to OrCAD Capture. A two-part fractured symbol set with the package net listing properties. Now that we've completed the export of the schematic symbol to OrCAD Capture, Let's move to FootprintBuilder. The standard FootprintBuilder part is completed, but in this case, as shown in red, I have several via variances. I will first select a set of non-propagated pins that I wish to turn into vias, taking those pins and propagating them, and moving to the pad stack calculator. First, selecting the pad variant tab, I will create a variant. Selecting the type of pad type to via and entering the pad shape, pad size, and hole size, I will regenerate and save the new pad stack as a variance. Clicking on the variance, I will swap the selected pads in the package view with the variant. I'm now ready to export the standard part with the via variances to my EDA tooling system, in this case Allegro or pads layout. Exporting the part directly to Allegro and bringing the part up in Allegro, I will note the via definitions and the pin definitions and the non-propagated pins in the center of the design. At any point in time we can select Generate, and the resulting variances will impact the following calculations, automatically updating any boundaries, keep out regions, or probe layers. We've now completed a complete fractured symbol set and PCB footprint land pattern model in a fraction of the time. Thank you, the EDABuilder development team.